About 10 years ago, at the birth of computer graphics, mathematicians started seeing extraordinary pictures appearing on their computer screens. Pictures such as this one, with all of this intricate detail. Or pictures such as this one, which also shows remarkable detail and complication. My name is John Hubbard. I'm a mathematician, and today I intend to tell you where these pictures come from and what they mean. I first ran into such pictures about 10 years ago when I was teaching elementary calculus at the University of Paris. 10 years ago there were computers, but there weren't very many and they were not available to undergraduate students. There were programmable calculators, however, and I cast around for a while to find programs that were sufficiently simple that one could in fact program them on a programmable calculator, and at the same time which led to interesting results. The most obvious candidate was Newton's method, an algorithm designed by Newton, therefore very old, and I thought at that time well understood. I will now explain to you, in the old-fashioned way, with paper and pencil, like Newton would have done, what it is that Newton's method does. Newton's method concerns solving equations, trying to find numbers x such that f of x is equal to 0. Graphically, this means the following. The function f has some graph that might look something like this, and the solutions of f of x equals 0 are the places where the graph intercepts the axis. Solving equations is something that everyone studies in school. More specifically, what they study is the solution of the quadratic equation, ax squared plus bx plus c equals 0. And everyone knows the famous quadratic formula, x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. You might think that if you want to solve some other equation, such for instance as sine of x plus 1/2 x plus 1/10 is equal to 0, for instance, that what you need is to develop an analogous formula appropriate to this equation. Unfortunately, that will not work. There are no formulas in general to solve equations. It is not quite true that the quadratic formula is the beginning and the end of formulas for solving equations, but it's almost true, and certainly the quadratic formula is the only one of any real use. In general, when you want to solve an equation, what you really mean is that you want to approximate a root. You want to find sequences which get closer and closer. Newton's method is one such scheme. You start with what you think is an approximate root, say this number. Call it x0. Well, of course, it isn't a root. But if you replace the function by its linear approximation, the function whose graph is the line tangent to the graph of the original function, and look at the root of that, you find a new point x1, which you might think is perhaps a better guess at a root of the equation. If you continue this way, starting at x1 this time, you are led to another approximation, x2, which actually at the level of this drawing looks as if it's perfect. But in any case, you could continue this procedure, and it is clear from the drawing that you will converge, and converge extremely rapidly to this root. That, of course, depended on having a good first guess, a good point x0 to start with. If you had started with a different point x0, say this point here, y0, then the process might have been quite different. This linear approximation goes over to this point, which would then be y1. If you continue the process, well, it certainly looks as if you're converging very nicely to a root, but you're not converging very nicely to the same root. Supposing I had started with some third initial condition, such as, say, this one, z0. Then the same sort of process might lead to that root way over there on the far left. Of course, if these three initial conditions lead to these three roots, then other ones in between will necessarily lead to some points which just can't make up their minds and never go to any roots at all. Therefore, it seems quite likely that when there are many roots to the equation, Newton's method will be quite difficult to understand. In 1886, almost exactly 100 years ago, a mathematician called Cayley published in the very first issue of the American Journal of Mathematics, which was the very first issue of any journal about mathematics ever published in the United States, an article in which he completely analyzed Newton's method for quadratic equations. Of course, it isn't very reasonable to use Newton's method to solve a quadratic equation because we already know everything about solving it. Still, it's a case to study, and in the last lines of that paper, Cayley announced that in a paper soon to be published, he was going to give a corresponding analysis for cubic equations, although, as he said, the case appeared to present considerably greater difficulties. Well, it certainly did present greater difficulties, so much greater that that paper, soon to be published, never was published. And in fact, I think that only very recently did we ever discover what it was that was really occurring when you tried to solve a cubic by Newton's method. I will now show you some slides which illustrate what occurs in that case. Here you see illustrated Newton's method for the polynomial z cubed minus 1. This polynomial has three roots, one in the center of the red eye, one in the center of the green eye, and one in the center of the blue eye. If you start your seed in any green region, red region, or blue region, you will converge to the root corresponding to the same color. In this picture, you have a slightly different cubic polynomial. Again, there are three roots. Again, there's a red eye, a blue eye, and a green eye. This time, fortunately, we are allowed an extra color, yellow, for none of the above. In this picture, which corresponds to yet another polynomial, there is again a yellow region. This yellow region, however, is considerably more complicated than it was before and will come to be a friend of ours. I call it the Towers of St. Mark because of its symmetrical shape with a large central piece and symmetrical pieces getting smaller and smaller on all sides. We will come to see this picture many times in the course of the show. In this case, again, there is a yellow region of seeds which do not lead to any root. But this time, this yellow set has quite a different structure from before. We call it the rabbit, perhaps in honor of Playboy. The body has 2 ears. Each one of those ears has 2 ears on it. There are infinitely many copies of this shape repeated infinitely many times with this tremendously complicated structure around it. Newton's method is an iterative scheme. You choose some seed x0, and then you set x1 is equal to f of x0, x2 is equal to f of x1, etc. Iterative schemes are very interesting. One problem with Newton's method is that it's rather a complicated one, even when the function that you are trying to find roots of is fairly simple. Although pictures of Newton's method were the first pictures that I ever saw that came out of iterating functions, they were sufficiently complicated that I made no progress in understanding them until I studied simpler function. The simpler function that was chosen was iterating quadratic polynomials, setting f of x is equal to x squared plus c. it's very important to realize that quadratic polynomials are the simplest functions that you could choose to iterate. Well, you could choose to iterate ax plus c. You could not have a square in there at all. But that leads to something very simple and uninteresting. This is the next case. And it turns out to be quite complicated enough. Let's see a few instances of this. Let us first consider the case c equals 0, by far the simplest in this subject. And if I set, for instance, x0 is equal to 1/2, you then easily see that x1 is equal to 1/2 squared, which is 1/4. And then x2 is equal to 1/4 squared, which is 1/16. And then x3 is equal to 1/16 squared, which is 1/256. And so forth. The sequence is clearly tending to 0. If you started with x0 is equal to 2, then x1 is equal to 2 squared is 4, x2 is equal to 16, and so forth. The sequence is clearly tending to infinity. These aren't the only two possibilities. If you started with x0 equals 1, then x1 is equal to 1, x2 is equal to 1. The sequence is just constantly 1. 1 is a fixed point of the transformation f of x equals x squared. If you started with x0 equals -1, then x1 is equal to 1, x2 is equal to 1, and so forth. After one move, the sequence becomes constantly 1. Actually, I am not going to want to consider this iteration only in real numbers. I'm going to want to study it in complex numbers. Why? Well, there are at least two reasons. The first one, and a very good one, is that it leads to much more interesting and much prettier pictures. A picture in the line, well, a picture in the line can never be all that fascinating. But a picture in the plane, that's quite a different matter. There is another and deeper reason, although it is not obvious. You might think that iterating in real numbers would obviously be simpler than iterating in the complex numbers. But it is not so. In fact, it is easier to study iteration in complex numbers than in real numbers. And this is true in the precise sense that many results which people wanted to prove about iteration in real numbers never were proved until complex methods were introduced. Let us see what corresponds to such sequences if we study complex numbers. Well, under the mapping z gives z squared, it's fairly easy to see what happens. All the points inside the closed unit disk under iteration converge to 0, and all the points outside the closed unit disk converge to infinity. Of points on the boundary of the unit disk, the behavior can be very much more complicated. We saw what happens at 1 and at -1. We saw that in these examples. What happens, for instance, at the number I? Well, I maps to I squared is equal to -1, which maps to -1 squared is equal to 1. So after 2 moves, it lands on 1. This brings up a very natural construction. The points inside the closed unit disk are the points whose orbits, the sequences such that if you start at such a point and consider the iterates, remain bounded. The closed unit disk is a set of points, the set of seeds which lead to bounded orbits. More generally, for any number c, you can consider the set kc of points which will have bounded orbits under the iteration of x squared plus c. One example is k0, which is the closed unit disk. This example is unfortunately extremely misleading. It is the only case, with one exception, which can be understood somehow in finite terms. For all values, except for 0 and one other exception, which is -2, the set Kc is somehow infinitely complicated. It is fractal. It is not smooth. If you blow in at some point, you start seeing over and over the same complicated structure. We have been discussing the process of iteration, of starting with a seed, taking some transformation. In this particular case, it's a quadratic polynomial, z squared plus c, applying that to the seed, applying the same transformation to the point that you get, then applying the transformation to the point that you get, and so forth, over and over and over again. I want to give a computer demonstration now of what this sequence of points called the orbit of the seed looks like. In this picture, you see illustrated what happens for the polynomial z squared plus c for c some very small number. So it will be just like the iteration of z squared. We saw that for the points inside the unit disk, the orbit is bounded, and for the points outside the unit disk, the orbit goes to infinity. Here is my seed, and I'm going to draw the orbit. There, it is bounded. As I move it, it remains bounded. As soon as I cross this black curve, it becomes unbounded. The black curve is called the Julia set, in honor of Gaston Julia, a French mathematician of the beginning of the century who studied these things. And it separates the points with bounded orbits from the points with unbounded orbits. And in this case, the drawing is exactly as you would expect for the polynomial z gives z squared. There are cases when the Julia set is much more complicated. Here is an example. It is still true that the black locus has an inside and an outside. If you start inside, the orbit, although more complicated than before, is bounded. That's inside this piece, or inside this piece, or inside this piece, or inside even this piece. Whereas if you go outside, there I'm outside, the orbit is unbounded and goes to infinity. This drawing and the preceding one may look quite different, but in one fundamental way they are very similar. The black locus is connected, consists of a single piece in that case, and it consists of a single piece in this case also. But there is another possibility, of which this is an example, where the Julia set, the black locus, instead of consisting of a single piece, consists of at least two, and in fact infinitely many. In this case, when you draw orbits, well, there isn't really any inside of this black locus, so the orbits all appear to go to infinity, and do in fact all go to infinity unless you start on the black locus itself. And the black locus is rather a strange set. First of all, it obviously consists of two pieces, this one and this one. But each of those further breaks up into several pieces. For instance, this one breaks up into this piece and that piece. And this piece breaks up into this piece and that piece. And that piece breaks up into this piece and that piece, and so forth. You can continue this process of breaking up forever and find that the Julia set actually consists of infinitely many, infinitely small pieces, infinitely many points, and there are no two points connected in it. I will next show you a series of slides and a video which will show you a collection of these sets Kc. I am sure you will be convinced from watching them that these sets Kc are indeed extremely complicated. Each slide contains all the information necessary to reconstitute it in the right-hand column. The name of this slide is J2, and in the right-hand column above J2 you see the date on which the picture was produced, JMNIN, the name of the program which produced it, 1 minute and 7 seconds, the time that the supercomputer took to compute it. Then you see the lower left-hand corner. You see a minus 0.2 E01. That should be read as minus 0.2 times 10 to the 1, in other words, minus 2. The lower left-hand corner is the point minus 2, minus 2. The side length is 0.4 E01, in other words, 4. So the whole frame is the square of side 4 centered at 0. The number of iterations is 1,000. The non-lin is a parameter having to do with the colors. The important number is this number minus 0.1 E01, in other words, minus 1. The picture concerns iteration of the polynomial z squared minus 1. Here we see a picture of the Julia set for the polynomial z squared. As we described, the points inside the unit disk have bounded orbits and the points outside go to infinity. This picture looks rather similar to the one we saw before. One solid blob of black. It corresponds to the value c equals 1/4. They can look more complicated yet. In this example, called the rabbit, there is a solid body with ears on it and ears on that. We will come to know the rabbit well before we're through. These pictures can be considerably more complicated yet, as this one shows, with lots and lots of pieces sticking out from a single point. This example, corresponding to c equals I, shows a strange filiform Julia set, filled with little dendrites sticking out all over the place. Despite the complications of these pictures, I want to show you that there is some order. Here is the Julia set for the polynomial z squared minus 1. I've called it the Towers of St. Mark. Try to keep it in your mind for a bit. Here is the rabbit with its 2 ears and 2 ears on it and 2 ears on it. Remember especially the shape of things with 2 things bifurcating off of it, with 2 things bifurcating off of it. Now, the next slides that I'm going to show concern ways of putting rabbits and towers together. Here you see a Julia set which looks a priori tremendously complicated, but if you look more carefully, you'll see that it is something where you have put together something like the towers, replacing each component by a rabbit. Here are the towers. Imagine replacing each body by a rabbit. This slide, on the other hand, is the opposite construction. You have the overall architecture of the rabbit, but each component of the rabbit has been replaced by the towers. There is the rabbit. Imagine replacing each piece by the tower picture. These pieces, rabbits and towers, can also be strung together in more complicated ways. Here we see, for instance, an overall filiform Julia set. But if you look more carefully at what there is in the center, you discover that there is a rabbit with all kinds of complicated structure around it. The pictures can also look essentially different. In this picture there is no black, but you can sort of guess where black should be, where the colors concentrate. We will see in a moment precisely when you have a connected black set and when you have one which breaks up like this one. In order to see many of these Julia sets, the following sequence is a film of how the Julia set varies as the number c takes a walk through the plane. The particular walk that was chosen is not at random, but it's not really a particularly orderly set, and you're seeing as a result a large number of very different Julia sets. Sometimes you see a set which is disconnected. It's always disconnected when the point in the center is in color. Sometimes you see nice, solid black Julia sets, like that one. Notice the way in which spirals connect and disconnect with variable number of arms. For instance, at the very moment, there are 4 arms. They swirl around and disappear. In not very long, you're going to see them reconnecting with 3 arms. There, they're coming together with 3 arms, swirling around in the other direction and disappearing. There are 5. And soon the pattern is going to become symmetrical and become very closely related to the tower picture. It's coming. There it is. We have been seeing pictures of these sets KC. There is the really simple one, the closed unit disk, but we've seen lots of others. Some that look like this, infinitely complicated but still more or less understandable. One that looked like this, also infinitely complicated but more or less understandable, and then others that were enormously more complex than this. If we had to understand iteration of quadratic polynomials by understanding each set KC individually and for itself, clearly our task would be hopeless. There's too great a variety. There are too many possibilities. Only if we can say something about all sets of KC simultaneously will it be possible to build a theory about these things. And it turns out that there is something to say about all sets KC simultaneously. Namely, there is a dichotomy which was discovered by 2 French mathematicians who really are the people who started this subject. Gaston Julia, and Fatou, Pierre Fatou. This dichotomy goes as follows. There are 2 possibilities. Either KC is connected, and that occurs if and only if 0 is in KC, or KC is simply a dust. And that occurs if and only if 0 is not in KC. The Julia set of the polynomial x squared plus c will be connected if the orbit of 0 is bounded. Here is the orbit of 0 in this case. You can see it clearly bounded. And it will be a dust if the orbit of 0 is unbounded. Here is approximately the orbit of 0 in this case. You can see it clearly unbounded. Now, the set of polynomials, that's the set of polynomials of the form x squared plus c, it is almost irresistible to try to draw the locus, the set of points C, such that one or the 2 alternatives occurs. And if you do try, you land on this picture. In this picture, the black points are the points for which the Julia set is connected. The color points are the set of points for which it is not. The black locus is called the Mandelbrot set in honor of Benoit Mandelbrot, who made the first analyses and the first good pictures of this drawing. Indeed, let us pick a black point. There is a black point. It is at approximately 0.397 plus 0.341 I. I will draw the Julia set for this value. Here, before your eyes, the computer is computing the Julia set. It's new and different from the previous one, quite complicated, certainly appears to be connected, and if I ask for the orbit of 0, 0 is approximately there. This is a complicated one, but you can see that this orbit of 0 clearly appears to be bounded. If, on the other hand, I go back to the Mandelbrot set and choose a colored point, let us say this one, and draw the Julia set for that value. Again, the Julia set appears to be something quite complicated, but you can see that it appears to be disconnected, and indeed, the orbit of 0 is unbounded. You can see also that it appears to be a dust. It clearly consists of two major pieces, each one of which breaks into two pieces, each one of which breaks up into further pieces, and that these pieces appear to get smaller and smaller. When we have a dichotomy, like the one I was mentioning, that either K sub C is connected or K sub C is a dust, it's almost impossible to resist the temptation to draw the set where one of the two alternatives holds. For instance, to draw the set M is equal to the set of C, such that K sub C is connected. And because there was another description of this set, namely that is the same as the set of C, such that 0 is in Kc, it is actually quite easy to draw this set. You take a point C, someplace in the plane, and you consider, for this point C, the sequence C, C squared plus C, C squared plus C, the whole thing squared plus C, C squared plus C, the whole thing squared plus C, the whole thing squared plus C, and so forth. If this sequence is unbounded, you are not in M, and if this sequence is bounded, you are in M. This suggests the following scheme. For every point C, compute this sequence until, say, it gets bigger than 10 or you've iterated 100 times. If you iterated 100 times and it still has never gotten bigger than 10, just leave the point C in black. Otherwise, color it according to the move on which it got bigger than 10. This is a color by number scheme. That extraordinarily simple program is the program which gives rise to the pictures that I'm going to show you next. The Mandelbrot set is tremendously complicated. You only come to appreciate this complication when you see it at greater and greater magnification. I'm going to show you several sequences of slides, each one of which consists of 7 blow-ups, each time near the center of the previous slide. At this magnification, it still appears that the Mandelbrot set is perhaps understandable, but now you can start seeing strange curlicues near the bottom, and at the center of these curlicues you will start seeing wilder and wilder objects. Here it is already beginning to look hairier and more complicated. Now it's starting to look perhaps even a little scary. And at the very center of this picture, you will see, again, shapes similar but more complicated than the ones that we had seen originally. Here is a new sequence of blow-ups. We're going to go and look between the ball that is sitting in the middle of the picture and the big body at the bottom. You see shapes reminiscent of the rabbit. That has to do with the fact that the rabbit actually is a point in the middle of that ball. Here you see serpentine shapes, and in the center of these serpents, you will find little copies of the Mandelbrot set. Here you see a little tiny copy of the Mandelbrot set, someplace embedded inside the Mandelbrot set. At this magnification, there are millions of them. Each one of these copies has its own peculiar pattern of decorations around it, completely individual and different from those of any other. Some sets are self-similar. The Julia sets that we've been seeing are self-similar. When you blow them up somewhere, you see over and over copies of the same thing. The Mandelbrot set is different. Every time you blow it up, you see new and more complicated things than what you had seen before. It is true, of course, that there are infinitely many copies of the Mandelbrot set within the Mandelbrot set, but that does not mean that the Mandelbrot set is self-similar. On the contrary, every one of these copies of the Mandelbrot set has its own extra special pattern of decorations around it, sufficiently special that you can discover which one it is that you are looking at if you understand the Mandelbrot set in an arbitrarily small neighborhood of it. Instead of showing individual slides to see blow-ups of the Mandelbrot set, one can also make a movie, at least if one has enough money or enough computer time. You see here a blow-up into a particular point of the Mandelbrot set. This blow-up represents fantastic amount of computation, hours and hours and hours on a supercomputer. At a large scale, the Mandelbrot set looks reasonably simple, but the closer you look at it, the more elaborate and complicated it becomes. Here you can already start seeing a serpentine shape on the tips of the decorations. At the very center of this serpentine shape is a shape that you will recognize again. Now the wiggle that we are concentrating on is clearly in view. And in fact, the point at the center of this wiggle that we are really looking for is beginning to come in focus. Now there is a black dot. Keep your eye on that black dot. It will grow on you. Now the shape is becoming recognizable. There's clearly a little Mandelbrot set there in the center. But this Mandelbrot set comes with a whole pattern of decorations around it of great beauty, and which belongs to that copy of the Mandelbrot set and to absolutely no other. We have been seeing pictures of these sets KC, and many of them looked tremendously complicated. I now want to outline how we can hope to understand them more or less completely. The idea, at least when KC is connected, is to imagine that you build KC out of a conductor. You then charge it, you let the little electrons in it flow to wherever it is that they want to go. They will create in the outside of KC an electric field with equipotentials and with field lines. In the case when C is 0, all that you have is the closed unit disk, and the equipotentials are, of course, concentric curves around it, whereas the field lines are radial lines. In other cases, it's much more difficult to understand precisely what this electric field will be, but trying to understand it is the key point to understanding the sets KC. Let us consider, for instance, the case C equals -1. In that case, we've seen many copies of KC. The picture looks essentially like this. And we have seen that the dynamics in this picture works as follows. There are two fixed points. One of them is here. One of them is here. This is mapped onto there. This is mapped onto here. This is mapped onto here. Unfortunately, there are infinitely many so that we do not run out. This is mapped back onto here. This is mapped onto here. These things are mapped further onto there. This is mapped over there, and so forth. Now, again, there are isoclines, there are equipotential curves created by the charged Julia set, looking more or less like this. And there are field lines, looking like this. The important thing to realize is that if we are able to say precisely when two field lines land at the same point, we will have given an almost complete description of the set KC. You should think of it then as given by some sort of a pinch disk. You start with a disk like that, and you squeeze down and squeeze down and squeeze down and squeeze down to create the squeeze points where field lines come down to the same point. Now, the important thing is that we do, in fact, completely understand when two field lines come to the same point. It requires a bit of describing to understand this. First, we need to give names to the field lines. Every field line goes off to infinity, and it goes off to infinity in some particular direction. It has some particular angle. These angles I am going to count in turns, and this one will be labeled 0. This one will be labeled 1/2. It's 1/2 of turn around. This one will be labeled 1/4. This one will be labeled 3/4. But what will be the label of this one? Well, there's a marvelous property which relates the dynamics of the polynomial z squared minus 1 and the angles of the rays of the field lines. Namely, if I take the ray at some particular angle theta, and I apply the polynomial to that ray, then it will be mapped to the ray at angle 2 theta. Notice that this is a relationship between field lines. Labeling these things by angles is a question of electrostatics, whereas saying that the polynomial maps one to another is a statement about the dynamics of the polynomial z squared minus 1. Well, this gives us some handle on what the angle of this ray is. We saw that this is a fixed point. Hence, this ray, which lands at that fixed point, must be mapped to another ray which lands at precisely the same fixed point. The dynamics does not move the end of the ray, and hence, well, you might think that it cannot move the ray, but actually that's not true. It can perfectly well map this ray to that one, and in fact, it has to map this ray to that one. For instance, because we saw that a point here is mapped to a point there, which is mapped to a point here, which is mapped to a point there, and so forth. Now, if this one has some angle theta, then that one has angle 2 theta. And then, since this ray is mapped back to that one has angle 4 theta. What are the angles which are equal to 4 times themselves? Well, I claim that there are precisely 2 of them. They are the angle theta equals 1/3 and theta equals 2/3. Well, certainly twice 1/3 is 2/3, and twice 2/3 is 4/3, but that's 1 plus 1/3, and that's 1 turn plus 1/3, so it's still 1/3 of an angle. We have now derived, simply from the fact that this ray lands at a fixed point, that its angle has to be 1/3. Okay, but that gives us almost a complete description of all the rays. For instance, what is the angle of this ray? Well, this point maps to that. Therefore, this angle theta has to be some angle such that 2 theta is equal to 1/3, and the obvious candidate is 1/6. This one maps to that one by the same argument. This one has to have angle 5/6. This point maps to that one, therefore this ray has to be a half of 1/6. 1/12 is the obvious candidate. This one has to be one of the halves of this one. The obvious candidate is 11/12. This point also maps to here. Therefore, these 2 angles also have to be halves of those angles. Well, how about this one? This one maps to this one, so it has to be one of the 2 halves of 5/6, and rather than being 11/12, it's 5/12. This one correspondingly is 7/12. This point maps to this one, so this ray is 5/24. This ray is at angle 7/24. Well, as you might imagine, you can continue this. I have sketched the complete rule for when rays at angle theta 1 and theta 2 land at the same point. In other words, I have sketched the complete structure of how this set is made. This discussion applied to the case C equals -1, which is a lot simpler than many. But essentially the same sort of arguments works to give a complete description of all sets KC. You can convince the computer to draw these equipotentials and field lines. In this particular case, for the polynomial z squared, the equipotentials are, as you would imagine, concentric circles around the disk. More interesting are the field lines, represented by the white bursts coming out of the disk. These field lines contain more information than you might expect, because you can figure out the angle where you are around the circle by looking at which field line arrives at which point. The field line at the right arrives at angle 0, the field line at the left arrives at angle 1/2, the field line at the top arrives at angle 1/4, And you can keep dividing by 2 by looking at the next intermediate field line. In the case of the towers, the equipotentials and field lines can be drawn also. Here the equipotentials look probably as you expect, and the field lines also perhaps look as you expect. But if you look more carefully, you'll see that there's a lot of information to be read off from them. More particularly, look at the point separating the main component of the body and the one to the left. To get to that one, you have to say first take the burst to the far left, then the one to the top, then the one in between these two. Then you have to alternately take the one to the right, to the left, to the right, to the left, to the right, to the left, if you want to zero in on that point. Now, this sequence, right, left, right, left, right, left, right, left, should be thought of as really the number in base 2, point 0, 1, 0, 1, 0, 1, 0, 1, and so forth, corresponding to the angle 1/3. In the case of the rabbit, it's also quite possible to draw equipotentials and field lines. The equipotentials again look as before. The field lines are quite different. If you try to come down to the point where the body and the 2 ears come together, you will notice that you have to follow a sequence of rays chosen by left, left, right, left, left, right, left, left, right, and so forth. In base 2, the point 0, 0, 1, 0, 0, 1, 0, 0, 1 is the number 1/7, and 1/7 is indeed the angle of the ray leading to that point. I want to understand in detail the structure of this Julia set. This is one of the simplest Julia sets. It's the Julia set for the polynomial z² - 1. We've seen it several times before. The dynamics of z² - 1 is a lot less symmetric looking than the polynomial is. And I want to describe in detail where various points go. We have seen that the Julia set is a boundary between the points with bounded orbits and the points with unbounded orbits when I move the seed outside. But what really happens to all these points? Well, the first thing to observe is that this point, right here, is a fixed point. It does not move at all. If I start an orbit there, well, I didn't start an orbit quite at that point, but you'll notice that the points, there are a lot of points right nearby, meaning that that point maps almost to itself. And there's another fixed point, which is this point over here. Now, the way this set maps to itself is as follows. First, this part maps to this part just by shoving over to the left. Then this part maps to this part just by shoving over to the left. Then this part maps to this part, also just by shoving over to the left. And fortunately, we have infinitely many of these little pieces as we go down here, so we never run out. We are always able to shove over to the left. That describes where all the points in here go. Now, how about the points over here? The best way to understand what they do is to imagine putting your thumb right there and then grabbing this end of the tail and pulling it over to there, so that this part goes on to here also, and then this part goes on to here, and this part goes on to there, and so forth, finally mapping the tip of the tail to this tip of the tail. That describes now what happens to this part of the drawing. In order to complete my description, I have to describe where this part of the drawing goes. Well, this point maps to here. This curve maps to the top half. Then all of these decorations up at the top map to this tip. Then this curve maps to the bottom. And then this curve maps to the top again. And then these decorations at the bottom map over to the tip again. And then this part maps back to the bottom. That tells us completely where all the points in this picture go. And in particular, note that if I start at a point slightly above this fixed point. The orbit consists of points which alternately are above and beneath the axis, tending to infinity. If I start over here on the real axis slightly beyond the point, the sequence just goes off to infinity in its own way. You can also get the computer to draw equipotentials and field lines for the Mandelbrot set. This contains all of the information about the structure of the Mandelbrot set that we have been talking about. In particular, if you try to go down to the point separating the main cardioid from the ball that's attached to it on the real axis, you will notice the same sequence of left rights, left rights, left rights, and so forth that we had been talking about in the case of the tower picture. We have seen how we can try to understand Julia sets using external rays, using when two rays come down to the same point. It turns out that exactly the same strategy can be used to understand the Mandelbrot set. It's much more complicated to make it work, but it does work. The first theorem that is needed in order to make this work is the statement M is connected. Therefore, if you were to make M out of a conductor, the remainder of the plane out of an insulator, charge your conductor and let your electrons just run around until they'd settled wherever they were going to settle, they would settle into some position and create a field on the outside. I want to sketch for you what this field would look like. This requires first drawing what the Mandelbrot set looks like, which is really a prerequisite for every lecture of this sort. So here is the Mandelbrot set. Please observe that the little curly cues that I'm putting on here are not drawn at random. They are actually the correct ones. Now I will draw in the rays at various angles. Here, of course, is the ray at angle 0. Here is the ray at angle 1/2. And that's more or less the end of the rays that are more or less obvious. It turns out that the ray at angle 1/4 is here. The ray at angle 3/4 is here. And now let me show you some rays which land at other distinguished points of the drawing. For instance, this point right here. The ray which comes down to it from the top has angle 1/3, and the ray which comes into it from the bottom has angle 2/3. How about this rather distinguished point? Well, the ray that comes onto it from that side has angle 1/7, and the ray that comes to it from this side has angle 2/7. Where are the other sevenths? Well, it turns out that there's a little Mandelbrot down on the real axis with this point at exactly -7/4. This is where the ray at angle 3/7 comes, and this is where the ray at angle 4/7 comes. 5/7 is there, and 6/7 is here. The next numbers to contemplate are the 15ths. Well, the ray at angle 1/15 comes in here. The ray at angle 2/15 comes in here. The ray at angle 3/15 comes to a little Mandelbrot approximately there. The ray at angle 4/15 comes to the same point. 5/15 is 1/3. We've already got it. 6/15 comes in here. 7/15 comes to a little Mandelbrot which is hardly visible at this scale, but I'll draw it in anyway. There is 7/15. Here is 8/15. 9/15. 10/15 is 2/3. We've already got it. 11/15. 12/15. 13/15. And 14/15. And that does it for the 15ths. Now, where does all of this come from? It turns out that a quadratic polynomial can have at most one attractive periodic point of any period. And this is the region where there is an attractive fixed point of period 1. This is the region where there is an attractive periodic point of period 2. The points where there is an attractive periodic point of period 3 are here, here, and there. The ones where there's an attractive periodic point of period 4 are here, 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 down there, in here, and in here. Now notice that the two numbers with 3 in the denominator landed precisely at the point where a component where there is an attractive periodic point of period 2 is attached. And 3, 1/3, written in base 2, is written as 0.010101, which repeats with period 2. 3, well, 1/7 is written in base 2, 0.001001, and it repeats with, the digits repeat with period 3, whereas the ray lands at a point where a component in which there are periodic points of period 3 is attached. 2/7 is 0.010010, which repeats. And more generally, all the numbers which have 7s in the denominators are those points which, if written in base 2, have digits repeating with period 3. 1/15 is 0.0001, which repeats. 2/15 is 0.0010, which repeats. There is this extraordinary relationship between the numerology, the digits of the angles when written in base 2, and the dynamics of the points where they land. It's rather hard to explain it for these angles, but I'm going to try to explain it with some precision for the point I. The point I is at the end of the ray of angle 1/6. And I now want to show you the relationship between the dynamics of the polynomial z squared plus I and the number 1/6 as written in base 2. Consider the polynomial z squared plus I. If you consider the orbit of 0 under this polynomial, 0 maps to 0 squared plus I is I, maps to I squared plus I, that's minus 1 plus I, maps to minus 1 plus I squared plus I. That requires a little bit of complex arithmetic to compute, but it turns out to be minus I. And minus I maps right back to minus 1 plus I. The following slide illustrates how the points 0, I, minus 1 plus I, and minus I lie in the set Ki. Here you see the Julia set for the polynomial z squared plus I. 0 is in the center. It maps to I directly above it. It maps to minus 1 plus I directly to the left of it, maps down to minus I beneath the center, then it maps back to minus 1 plus I, bouncing back and forth with period 2. If you write the number 1/6 in base 2, 1/6 is equal to 0.0010101, which repeats. I've written it so that the similarity of these two expressions can easily be seen. 0 after one move lands on a periodic point of period 2. In the digits, after one digit, it repeats with period 2. The parallelism is evident. It turns out that this is a completely general phenomenon. It is always true that the digits in base 2 of a given angle reflect the dynamics of the polynomial lying at the end of that ray. It's easy to believe that if such a property can be established, you then can understand when two rays land at the same point. It requires, of course, that the corresponding digits have somehow similar properties. The rules of this have, in fact, been completely worked out, and this allows one to give a complete description of the Mandelbrot set. Despite all of those curlicues, all of those spirals, all of that complication, we can give names to every single point of the Mandelbrot set and describe its dynamics down to the finest detail. Here is a sequence of blow-ups in the parameter space for an altogether different family, Newton's method for cubic polynomials. In the large, we see a picture very similar to the pictures that we saw for Newton's method for individual polynomials, very simple with three large shapes. But if you blow up along the edges, you start seeing more complicated things. This shape, which I call a Mandelbug, still in honor of Mandelbrot, and at its head, you can see what is clearly a copy of the Mandelbrot set. If you further blow up that Mandelbrot set, you see a shape which, if it's colored slightly differently, if you color it so as to color simply according to the speed of convergence to some root, not caring about which one, you see this picture, which is remarkably similar to the corresponding picture for the original Mandelbrot set obtained iterating quadratic polynomials. Even if some mathematical parts of our discussion have eluded you, there's a philosophical point in this that you really should understand. The drawings that we have been seeing, even the most complex ones, are all produced by incredibly short and simple programs. Incredibly in the sense that they are 4 or 5 lines long, very much shorter than a program that does, for instance, word processing or accounting, perhaps the same length as a program which just draws a square on the screen. It is not at all obvious that it is possible to create tremendously complicated objects out of such simple rules. And it comes as a great surprise at first that this is possible at all. Yet there is in nature an example of tremendously complicated things being produced by very simple rules. And that example is all living things. Indeed, all living things are constructed from a linear programming, the linear program, and the linear program is DNA. We can easily measure the length of the DNA program which gives rise to any particular living thing simply by weighing the DNA in question, and you find that a virus has approximately 20,000 bits worth of DNA, whereas a vertebrate might have as many as 1 billion. That may sound like a large number, but it most definitely is not. If you consider, for instance, that we have about 20 billion nerve cells, not to mention the many hundreds and thousands of billions of other kinds of cells that we have in our body, every one of which contains a large number of things, in particular a complete copy of the DNA, a complete copy of the program that gives rise to the organism, you start seeing how extraordinarily more complicated the fully grown organism is than the DNA which gives rise to it. Thus, I think you should really think of my pictures as some sort of a metaphor for living things. Imagine, for instance, that these pictures had just dropped from Mars on Earth about 50 years ago. What would people have discovered about them? They might have classified them according to the kinds of curlicues, the types of spirals, the kinds of connections that they had. They would have come up with some complicated botanical description of all the various pictures, and still wouldn't have been anywhere near a real understanding of what gave rise to them. It is therefore a real message of hope. Possibly, biology can really be understood in the same way that these pictures can be understood. Possibly, the program in the DNA is enormously simpler than anybody imagines. If it were true, there is no reason to think that anyone would know it. I do not think that without having started with the program and ended with the pictures, anyone would ever have discovered that these pictures are really created by a simple program. I think they would have gone on classifying them forever according to their macroscopic properties without ever coming to terms with their very simple origin.